Okay, cool. So I'm going to go through the Java native image stuff. I've not used this in production yet, so it's like a learning experience for me. Right. Going to go through some of the simple what, why not, how to do it, and then a demo which will probably fail because I'm going to do it live, and it failed earlier today. So the Java native image is part of a thing called, I think it's GraalVM, don't know how to pronounce it. So it's a new JDK from Oracle. Originally started as a research project. So it contains a normal JVM, a normal Java compiler, all the normal tools you can use to run Java applications, with what they call an advanced JIT compiler. So you can run and compile Java applications just as normal. It also contains a thing called the Truffle framework, which you can use to write language runtimes in Java. I'll cover that a little bit, but that's not the main focus of the talk. The third main thing it contains is this native image stuff, so you can compile Java down to a native application executable. And there are community and enterprise editions. So I think this is one way Oracle are trying to monetize the JVM. There we go. I'll cover Truffle first, mainly because we can kind of get out of the way and then ignore it. So it's a way, I think this is originally how the project started, actually. A bunch of people trying to rewrite the hotspot VM in Java, because it's written in C++ at the moment. So it's kind of evolved into a framework that you can use to write programming language implementations in Java. So they've got implementations of Java itself, R, Python, really, JavaScript. They run with varying levels of compatibility with their normal runtime versions, and varying levels of actual performance. So I think the Java one is 2 or 3 times slower than running actual Java with a real JVM. I think the interesting point here is probably that you can run the different languages kind of together and they can interoperate in a fairly performant way without going through JNI or anything like that, sort of kind of native Java. So one of the other things that's probably slightly interesting with it is that you can run a different Java context. So you can run Java 8 code on a newer VM, so that it is in theory more compatible. I don't know how useful that is in production. I've not done it. But I'm kind of covering this because it's part of the GraalVM stuff, but it's not really involved in native. I don't know how many people are using this, to be honest, because I know there are other projects to run Python and Ruby as JVM languages. But this is so you can do it all in Java. Right, the native image stuff. So this is the main bulk of the talk, hopefully. So normally Java, you write Java code, it compiles to a bytecode, a platform agnostic bytecode, and then you can run that bytecode anywhere that you have a JVM. So you can run it on your phone, on your toaster, on Linux, on Macs, everywhere, you don't really care what the target is as long as it can run Java bytecode. So that means that the compile time optimizations are fairly limited. It can't do a great deal. It just kind of compiles everything and does a bit of syntactic sugar magic, and just kind of shovels it all in. And the optimizations really happen at runtime, where the hotspot will compile and optimize based on actual real usage. So it can do inlining, it can remove blocks, it can more aggressively compile code to native code instead of interpreting the bytecode, things like that. Native image just does ahead of time compilation to produce an actual executable for the target platform. So more like the way you produce a Golang executable. So that means that it's not run anywhere, it's run on the thing you're compiling for. It doesn't run, there isn't a separate JVM, it's just a single executable that you run. So you don't have to install a JVM anyway. And it's got kind of different memory management, thread processing, garbage collection and stuff. They call this substrate VM. I'm not sure why, but it's from an application point of view, it kind of looks the same, but the way it runs is completely different. So why do this? It starts up faster. It starts up a lot faster. For a lot of small applications, you have lower memory usage because it can do more optimizations and removal of dead code and things at compile time. And the runtime only contains the stuff that it really needs. You don't actually need to install a JVM everywhere, which can be a pain, depending on what package manager you're using. If you're used to doing quite small microservices, if you try run a standard Spring Boot app, you're looking at hundreds of megs of memory. It's not particularly micro. So it's better suited for actual smaller microservices that start up quicker. And if you wanted to do some of the functions of the as a service stuff in Java, it makes it a bit more realistic. I'm not sure it makes it a good idea, but it does make it more realistic. And there's support by a lot of common Java web frameworks. So it's not completely on the edge. So why not? Why is it a bad idea? You can't compile everything ahead of time. So lot of code that uses things like lots of dynamic reflection, dynamic proxies, native access. You'll need to help it compile so that the ahead of time compiler knows what you're doing. Otherwise, it'll just not include the code and you just get exceptions at runtime. So things like Spring, which does an awful lot of all that stuff I just said, needs a bunch of help to do for this to work. So the framework support is really essential. And so the more stuff you start including, you're probably going to find more edges that don't quite work native. There's only the basic serial garbage collector. So if you actually want to do large applications with big heaps or lots of threads and stuff like that, you'll probably struggle. And not every application really support is a good idea for this. It's not running Java bytecode, so the normal Java debugging tools you might use, so profilers, debuggers, thread dumps, all the tools you might use to talk to running JVM, they're all out the window. They're all gone. So being able to try and use the tools that you've come to know and hate they're not going to work particularly well. There's a bunch of stuff behind the enterprise version, so better garbage collections, supposedly better heap and compiler optimizations. It's unclear what those are or how they're better, but it does seem to be one way that they're trying to monetize this. And you can compile stuff in Macs, Windows, Linux, ARM, I think is in kind of slightly less supported. Other platforms they don't particularly care. So if you want to run stuff on BSD or whatever, you're out of luck. So how do you do it? So you can compile just something to bytecode using Java compiler as normal. You can then run this native image tool, which comes with GraalVM, and that will give you your native application. So installing GraalVM and the tools seems to be a bit fiddly. You install it and it gives you an updater tool, which you then have to use to install everything else. And I've not found a very neat way of doing that. And you also need a lot of the kind of, because it's compiling stuff to native code, you need all the compiler support for your platform. So depending on what you're doing, what platform you're doing, different tools you need.
Do you have to compile it on the platform you're targeting?
As far as I can see, yeah. I think there are people talking about doing cross-compilation, but it seems to be not very well supported. I think there's some people trying to use Docker images for that side of it. It's not something I've looked into in much depth, to be honest. I did a quick Google and lots of people having pain doing that.
And when you really, really, really need it, do it.
Yeah, I mean, I think cross-compilation is a bit fiddly at the best of times if you're writing C and stuff like that. So I imagine it's even more fiddly with this. So one of the things that you need to do if you're running a vaguely complex Java application is tell the native image process what things it can't work out. Because when it compiles the application, it tries to work out what you're doing. It tries to work out what flexion you're doing, what classes are in use, what methods and fields are in use, and all that stuff. It can do that with normal code that looks normal. If you start doing dynamic stuff, it's going to need help. So you can feed it a configuration file at runtime, at compile time, sorry, which tells it which classes, which fields and stuff you're actually going to use. You can add you can run it as a normal Java application, so not native, and run that with a Java agent, and it will spit out all the stuff that you're doing dynamically, which you can then feed back in to the configuration file that you would use to your native application. It's a bit, I think if you're doing this all by yourself, it's a bit fiddly. So this is an example configuration file. So this means that if this platform-dependent zero class is available, if it's reachable, then I need the unsafe field from the JavaMist unsafe class. So it basically tells the ahead of time compiler to definitely include this in the binary when you create it. Or you can do this in Java. So you can implement this feature interface from the GraalVM native library, and this will get run during the build, and it will then tell the build system that I need this class, these fields, all this other stuff. Most of the stuff I've seen from Spring and Jetty and other things uses this approach to do it in Java, because I think then you can reference classes properly, and the classes move around or get renamed. It's a bit more refactoring friendly. There we go. So I look at Micronaut first. So Micronaut is a similar, if you've not used it, it's a kind of smaller, neater kind of version of Spring Boot. It does everything. It doesn't use reflection. It does everything at build time or injection and stuff like that. So it's a bit better placed really to start with native image, because it doesn't do as much reflection and proxies and stuff like that. So they've got support for a lot of their sort of libraries. So database access, web services, RabbitMQ, distributed tracing, lots of the stuff you might use in microservice. Some of the other libraries that support is variable again, so I think you'd need to really work out whether what you're doing is supported properly. It includes an annotation processor, a custom annotation processor, so you can stick some annotations on the classes too. So you don't have to write those configuration files I was telling you about before. You can just stick a few annotations on it, and it will generate them for you. So you basically say that, yeah, I need this class to definitely be used because it'll be picked up by reflection. Spring Boot has a lot more work to do, but Spring's a bigger project and they've done a lot of that. So there's a Spring native project, so that supports a lot of the Spring projects you've got already. So the normal web services, reactive web services, a lot of the database access, metrics, message queues, all that stuff. In a similar way, you can make it generate the native type hints with annotations. So basically say that this class is used and these fields are used and that stuff, and it will generate them for you. So that is about it. So that is not too much information, really. I will start with Spring Boot. So here's a project I prepared earlier. This looks like a fairly boring standard Spring Boot application. So we inherit from the starter. We depend on various other starters for JDBC. We ignore the version of Tomcat it ships with, because we need an experimental version of Tomcat, which works with the native stuff. Again, there's another bit of native bits there. Otherwise, it kind of looks the same. So I've got an HT database, Lombok, tests. There's a bit of, or a lot, depending on how you view it, boilerplate stuff to stick in the POM to make it do the compiler. So there's a Spring Boot plugin where you tell it, whatever that means, I'm not sure, it's just a bit of magic you have to shove in. And there's an AOT plugin as well, which picks up their annotations and generates the native parts. The application itself is very simple and doesn't have anything native specific in it. So there's just a controller, service, database, bunch of standard stuff. Okay, so we run the target Spring Boot build eventually. There you go. This is going to take a few minutes. So what I'll do is I'll carry on with the other one as well. Because it's not very interesting to sit here for a few minutes and watch just that. So I'll start the one for Micronaut at the same time. So Micronaut, we're doing a package and we're passing this, telling Maven to use native image packaging. So it's a bit less custom for Micronaut, I suppose. I'll show you the Micronaut project itself. Again, this is a fairly standard Micronaut project. There's a parent. We depend on a few standard features. There's less kind of custom native stuff in here. It just kind of works. There's a bit of boilerplate for the compiler and passing some Micronaut native stuff, but there's a lot less happening here because Micronaut's just a bit more well suited to doing this kind of project. So if we look at the actual code here, there's nothing native specific going on here. There's this introspective, which is a standard Java bean. Well, no, it isn't actually. It's that's kind of required by Micronaut anyway because it does this stuff at runtime. It doesn't do this stuff at runtime. So this is just a standard Micronaut service. We're not doing anything special. So all we're doing specially is at compile time, we're telling it to be native. And it wanders off and does a whole bunch of making my fans spin like crazy stuff to you see it running the analysis of the actual application. It's picking up some of these features. So the Java feature stuff I showed you earlier, where people register their collective accesses. So there's a bunch of these for Netty, for Hibernate, for JDBC, stuff all in Micronaut. So it kind of comes with these for free, almost, whereas Spring, you have to kind of drag in a bunch of this stuff. Okay. Oh, this one has finished. Right, there we go. So we can, that took 2.5 minutes, which is quite a long time. So we've got a bigger, yes. So we've got big enough?
Yeah.
So here we've got that is the native binary. It's quite large. What's that? So the native binary there is 90 meg, give or take. And the jar was 21K.
And it was just a resting.
Yeah, that was it. So there you go. But we can run it as a native binary. Here we go. Allow. And that is running. So that's quite quick. Micronaut's a bit quicker than Spring anyway, but that is pretty quick to start up and do some very exciting testing. And go. It works. It's really good. It returns a random bit of stuff. Doesn't really matter what it does, to be honest. So that is, I think, it's quite interesting in terms of producing not a small file, but fairly quick to run and quick to ship around binary. So look at this one. This one's finished too. 8 minutes, lovely. So the Spring one, the Spring. Spring one doesn't seem to generate a native binary. That's helpful. It's turning into native binary as a Docker image. Oh, I give up. Yeah, so let's see if we can run this. I must admit, this was broken this morning, so I haven't tested it today. I tested it when I was originally scheduled to do this talk several weeks ago, and I've forgotten how to run it. Yeah, it's produced a Docker image containing the binary, which seems a bit pointless, doesn't it? Not sure why it's done that. But I suspect, I mean, the jar file it created was 20 meg there, and so I think that's the jar file containing all the Java code that it needs, including dependencies. So I expect the native ones even bigger, the actual native one. That's kind of it. My takeaway from this was don't do this with Spring unless you really have to. It seems a lot more painful. I'd do it with a framework that's a bit more happy and native and expects a bit more, natively happy with native, I suppose. That's it, we're done.